I can. I would like first to thank the organizers. I'm very honored to be here and very happy to participate to Carlos' anniversary conference. I will speak about a subject which has been initiated, I would say, for us in 1997 around, at the suggestion of Jean-Pierre Puel, and we began working with Carlos in University of Versailles at that time on this subject, and then we continued in various aspects of this field. This implied a lot of travels to Chile, where we're doing this kind of activity. This is Jorge San Martin, which is one of our main collaborators in this field, who is not a very great traveler, so he didn't make it. And also we visited wonderful places like Valparaiso with the same opportunity. Now, another way to design this field is a study of particulate flows, which are rigid bodies inside a fluid. So the main features of this, let's say, kind of problems is that you have some fluid dynamics equations. In our works, they were often the Navier-Stokes incompressible equations. In a domain FFT here, filling so a bounded domain, and in which there are some particles or some rigid bodies Si of t of various sizes. So if the bodies are rigid, which will be the case in most of my talk, these objects are governed by the ODEs coming from the Newton's laws. And the main difficulty, let's say, to be tackled is that we have a free boundary value problem, in the sense that the domain filled by the fluid is variable in time, and that this variation is not a priori known. Okay, the first results on this problem, I don't know if there was a lack of interest or people did, because I think that people had the mathematical means to tackle this long time before. But the first published results are around year 2000. Let me mention some early contributions here, which are not maybe the first one, but is at least to my knowledge. So Hoffman and Starovoitov, Desjardins and Esteban, these are weak solutions, the first two references. The third one of Céline Gramont and Yvon Madé concerned strong solutions. And then there were some papers in which participated our group in connections with a group in Santiago de Chile, and in particular with Carlos. So we can associate to this situation also control or identification problems. So for the control, let us look to the right. Here we can act by a force on the solid and want to steer it in a final position, and also in the same time to steer the fluid to rest. And there is also identification, which I will finally not speak about because I realize that my time is not long enough. So in which we measure something on the boundary, for instance, of the domain as a part of the Dirichlet to Neumann map, and we want to localize the solid and also to identify its shape. This is a field in which Carlos has important contributions, namely with people also in our university. So, in fact, I will focus on the first two points here, existence of solution and some control problems. So, I will first give a kind of personal perspective of the existence theory for these problems. So, the equations are here. Navier-Stokes equations, incompressible Navier-Stokes in the domain f of h of t. So h of t, so I suppose that here, for the simplicity, I'm in 2D, and my rigid body is a ball. h of t is the position of the mass center of the ball. So the domain filled by the fluid F depends only on the position of the ball, which is denoted f of h of t, which is unknown a priori. So I have free divergence, no slip conditions at the exterior boundary, and also at the interface of the solid and of the fluid. And then for the solid, we have the Newton laws. First one is for the linear momentum, whereas the second one is for the angular momentum. So here it's written in 2D. Okay, so there are various approaches to existence, uniqueness, and other more subtle properties of these systems. But somehow I tried to find some common points. First, most of the methods reduce somehow the problem to a fixed domain, which looks very natural. This can be done in an exact manner by change of variable, as I will show later, or in an approximated manner. I will also discuss briefly this approach. Then we have to come back. If we did approximations, then we have to show some convergence result, some compactness result at least. And finally, one can look if under some assumptions like 2D or like small data, our solutions will be global in time. So, and in particular, that they will not, that the rigid bodies will not touch, for instance, the exterior boundary. So first, one word about L2 penalization, which is a method on which we originally focused in the work with Carlos. So here, the fluid solid domain is omega, in which you have some rigid body inside. So this is fluid plus rigid. The main idea is to put this in a big box denoted capital A, and then to do a change of variables which will fix the body. In this case, if you fix the rigid body, of course, what will move by a translation, by a simple translation, will be the exterior domain omega, which is denoted omega minus h. And then what we do simply is that we write a kind of Navier-Stokes system in the whole A, and we put penalty in the part which is not in omega minus h. So if we want to write the equations, what happens? There is a blue term, the h dot. So this is not working well, but okay. H dot, which comes from the change of variable, is just a translation here, a transport term, and is a red term, which is a penalization term, which is aimed to make the velocity 0 outside my variable domain omega of h of t. So this is, here doing this kind of approach has the advantage that the interface of the penalized region is a region where velocity is 0, and it makes it easier to look to compactness after. Because, of course, one could do penalty in a different way. One could somehow penalize in the ball by rigid motion, which has in fact been done much later. And in fact, in those numerical approaches of Georges-Henri Cotet, Bergman and Yolo, and the group of Maury. So the penalty is an L2 type by slightly different, and it's used essentially for numerical purposes. Let us also mention that if the obstacle is fixed, this penalty approach is also quite recent. It comes from a paper Van Gogh, Bruno, and Fabry from 1999. Another kind of penalization is what could be called H1 penalization, in which, in fact, the solid, the rigid bodies are replaced by very viscous fluid. So we take a viscosity, roughly speaking, which goes to infinity in the rigid bodies, and then we have to pass to the limit, which of course makes a lot of difficulties, but it can be done. And this was the original approach, our original approach in getting global existence of weak solutions in the two-dimensional case. And also Feiereisel had performed a generalization in the three-dimensional case. So what about this global character? Global means here, of course, in the sense of Navier-Stokes, global, it could be global in 2D, or global for small data in 3D. So where the results are more, or even global existence in 3D of weak solutions. This also makes sense. So we try to recreate all the theory existing for Navier-Stokes in this case. So let me just discuss briefly the 2D case. So here there are some function spaces which everybody working on Navier-Stokes knows, V and H of omega, and then we have a space K of key, which is the space specific to our problem. So we replace the rigidity constraint by the fact that the stress rate tensor D of V is equal to 0 in some subset. And then we are able to show that, in fact, so this is a natural function space. And then we are able to show that we have more solids. Then my characteristic function will be the sum of key I. Then if I have two of those ones, and if two solids are in contact, then they have necessarily the same rigid displacement. So in other words, if my velocity field is globally H1, it's rigid in one solid and rigid in the second solid, these solids touch in a point only, then they have the same rigid velocity field. What does it mean physically? If two bodies touch within this theory, they can touch only with 0 relative velocity. So in the general setting, there is no better result for the moment. So here is a formal statement. But in particular geometries, a lot of people like Esla, Hileret, and Takahashi showed that in fact the touching never occurs. So within the Navier-Stokes theory, if you throw a ball and let it fall, it will never touch the bottom, which of course looks very strange, but you have to think it's within the Navier-Stokes theory, which is no longer then valid at very small scales. And also, let us mention that somehow approach which mixed the two one I mentioned here was given by Esteban and Desjardins, where what they did, they took very regular approximate solution, they constructed very regular approximate solutions, and then they passed to the limit in the energy space. So what about strong solutions? So not a very nice picture. The idea is to do a change of variables, which is very natural, which is a rigid displacement around the body, and which is the identity near the boundary. And moreover, this one should be volume preserving because you want to conserve free divergence condition, incompressibility condition. And this is done in fact using a certain change of variables, constructing first a velocity field which is just a translation around the body and which is equal to 0 close to the exterior boundary, and then taking the integral curves of this system to construct the diffeomorphism. So another choice would be just to take as lambda the velocity field of the fluid. This means passing in Lagrangian coordinates, which has been essentially done in this context by Yvon and Céline Grandmont, following the general, let's say, approach of the Russian free boundary problem school. Now some control problems, which is the recent part of the work I'd like to present. Now let us see, can we control all these let's say, systems, which are, as you've seen, highly coupled, nonlinear, and so on. First, I have this situation. I have a rigid ball in a fluid, and I want to steer it from initial position H0 to initial position H1 by acting with a force on the fluid, on the solid. So in other words, if I look to my system, it's the same as before, with the exception of this equation for mh double dot, where I add a control force u. So I want to do this in 2D or 3D, and also to avoid to touch any boundary, of course, when doing this job. So it's more or less a feedback, not exactly, but almost a feedback law, which we will find. So we take the total energy. We look what we know very well, which is its derivative. And then, in fact, we perturb it by adding something like a fictitious string energy. This is the potential energy of a string, which we add, which should connect my current position h of t to h1. So my control u will be nothing else but an elastic force pushing, steering my body to h1. And so with this calculation, so the energy I will work with will be w of t, the real one. And then with these formulas, I see that to make w decreasing, what I have is to choose u, what I can, I wouldn't say I have, what can be natural, is to take u in this form, and without surprise, what I get is an elastic force and a damping, possibly, but the damping coefficient kd can be 0. Okay, but of course, looking back to my picture, I cannot do it globally. I have to do it locally, because to go from h0 to h1 in this geometry, it would not be possible to do it directly. Okay, so with this, we are able to prove by a simple calculation, formal one, that if h1 is somehow closer to h0 than to the exterior boundary, then everything is okay. I will not touch the boundary. I have global in time existence. And using a code which is due to Jean-Francois Schede, we can see how these things could work. So I gave some stations. I design a traject. I choose some stations. And at some station, I'm putting a string, a virtual string, and which is switched as soon as we arrived in the neighborhood of the right point. So here we can describe, and at the end, I don't know if this simulation will reach the end, the fluid will be very close to 0. So this is done in a somehow stealthy way. The velocity of the fluid does not become very large at the beginning. At the end, even it tends to 0. So now, what we'll do, I want to go from the upper point to the lower one, but my initial velocity is in another direction. And so this is just the trajectory of the body, accelerated. And if we want to see the same with the fluid, it is normally the same. We see what happens in a very simple geometry. Here there is only one feedback. Here it's really a feedback law, which I put that string force. Okay, so this, which is simulations, can be proved rigorously. Somehow there is a nice dynamical system which combines Navier-Stokes with a finite dimensional one, and we can use tools like invariance principle and others, taking a lot of advantage that a part is finite dimensional, taking a lot of advantage of the fact that the finite dimensional part has a lot of compactness property which can be used. So in 2D, somehow, if I choose correctly my parameters, my result is global and for every initial data. Whereas in 3D, I have to make assumptions, as usual. If my initial data is small enough for given elastical constants, all this works locally, and then by iterating, it will work globally. And I will end up with another kind of control, which is much more complicated, in fact, where the control is no longer here. In fact, if you look, somehow we have to act from the exterior on the body to control the system. We have to push the rigid ball. But what about self-propelled, namely fish-like swimming? Here, my deformation is, my control is the deformation of the object, but which will be imposed. It's still somehow rigid. I have no elasticity theory here. I impose the displacement of the rigid body, which should satisfy some conditions to be physically consistent, which are called self-propelling conditions. And the main ones are, roughly speaking, that if you put your object in the empty space and it begins deforming, this deformation contains no translation, for instance. It will not be able to swim without water around him. So with these restrictions, we are not able to do really control theory. We are able to show that our problems are well posed, and also taking some deformation laws from the literature, which is either biological or scientific computing literature, and computing for Reynolds number high enough, otherwise you will see nothing. We see that these objects swim in straight line. We can do also several because we use a fixed mesh method, which is highly independent of the number of bodies. And moreover, we can make it take some, let's say, very simple curved trajectories by adding a constant term in the curvature. So I think that, I hope I was not too short. No. Okay.
And thank you very much.
Thank you very much.
Questions if you have or comments.
Yes, I have one or two comments or questions. The first one considered the uniqueness problem. For the uniqueness, you have nothing.
In the usual result in 2D, as far as you are far from contact in 2D, there is uniqueness. It was formally written recently in a paper of Olivier Glass and Frank Sueur. So 2D, and no. If you in the presence of context, there is exactly the contrary. You have no uniqueness, and this has been shown by Feyerabend.
Yes. My second question consists of I would like to know. I am thinking of the inverse problem. So, what happens if you put the control on the boundary, on the external boundary? Because inside the fluid, it is impossible to act.
Yeah.
Practically. So if you put it on the boundary, do you have something?
Yes, somehow there are results with internal control. These results are on the side of Takashi and Imanuvilov and of Bulakia and Osses, which is here. And these results have an internal control, but doesn't matter because for this problem in the fluid, you just make a bulk as usually, you extend your fluid domain, and then this will give you a boundary control. Okay. So boundary control of the fluid structure system is available with the same restriction as for Navier-Stokes. It has to be local for small data.
Let us thank again the speaker. And,
thank you very much.
Thank you. First, I want to thank the scientific committee and the organizing committee for giving me the opportunity to give this talk, and in particular, the one who were in both committee, Enrique Zuazua and Grégoire Allaire. And of course, it's a great pleasure for me to celebrate this birthday, Carlos' birthday. I am very impressed by the work he has done, and I will present some of his works now first. So this is a picture where you see Carlos. We come back to this picture later on. I'm very impressed, as I told before, by various results obtained by Carlos. And for example, I like very much also his books, his book on fluids and periodic structure, and especially the chapter 3 of this book, which is on this aspect of homogenization in a fluid structure problem. I appreciate also very much this paper on Stokes and Navier-Stokes equation with boundary conditions, which are very interesting, involving the pressure. It's very nice. It's a seminal work. And also this paper, which was mentioned first this morning by Marius, on the equation of Navier-Stokes equation, where there is a rigid body inside the viscous fluids. So this is also a very important contribution to this subject. So I take 3 papers, but of course there are many others. And so this is very excellent result. And I would like to mention that, of course, when you do research of such a quality, you must be very clever and bright and so on, but also have some very important assets. And one of the assets is Lola, who is here. The second asset that I would like to present you is Jean-Pierre, who was a Carlos advisor. And the third asset that I would like to present you was already, in fact, on the previous slide. It's, you see, Carlos has made many contributions, very seminal contributions on fluid dynamics. And so this is thanks also to his laboratory that you can see here. Yes? You see, this is a secret one, so the quality of the image is not very good. And you see only part. Of course, the key part is here. It's not here. It's not. So I would like to speak about the regulation of some rivers, La Sambre and La Meuse in Belgium. But first, I would like to start with the first regulation, which was done at some industrial level. And this is the Watt regulator. This is the engine, the Watt Boulton engine that you can see in the Museum of Sciences in London. The date is 1788, and the regulator is here. So thanks to this regulator, Watt succeeded to have a constant speed for his engine, whatever is the load, even if the load is changing during time. So this is a drawing done by Watt, and I'm going to explain briefly how is it working. So you have this device which turns around the vertical axis at a speed which is proportional to the speed of the engine, the steam engine. So when the velocity is increasing, then the two balls are going upward and outward, and thanks to this big linkage, then there will be less steam going in the steam engine, and then the speed is going to decrease. And in the converse, the speed is decreasing, then the two balls are going down, and thanks to the linkage and the beam linkage, there will be more steam going in the steam engine, and the speed is going to increase. And I would like to show you a movie. This is a fiction, in fact. But it's important to see that even in fiction, you can see this type of regulators. This is a movie I'm at by Edgar Wright. So we are going to see this. For the first experiment, there will be no regulator, and you can compare the situation to our life when we are doing research. There is some idea. We have some idea. The idea is going up and up. It's improving what we plan to have, but there will be some problems. So there is also something which is very interesting. This is we will see some very good stroboscopic effect on the wheel. So you see, the idea is progressing. You have more speed. You try to improve. Yes. It's getting better and better. And we are very happy. Yes. We are very happy. Things, and a little surprised in some sense. Yes, it's getting very good. And this is the happiness. Yeah. We want to share our happiness with other people. We knock at the doors, and then we dance. We dance, maybe only in the mind. Yes. Yes. Yeah. And you see, we will see what happened in some other office where another researcher is doing some research on something else. Here is the other office. And then there is a blow up because there is no regulator. And then you try to do something more in order to make the idea working. And then you look to some books and you see this device. And you try to apply this device to your idea. And now the device is here. You see it here? This is the watt regulator. And now everything works well. But there is something which is a little strange, is that the researcher doesn't seem to be as happy as it was before, yeah, when it was not working. So we are going to apply this.
Were you involved in the movie in some way? Or?
No, not at all, no. So we are going to apply this method, try to regulate the water level in the river La Sambre in Belgium. So this is the river La Sambre in Belgium, and you see a map from above, and there is the control. Where is the control? You see, before it was you act on the valve. Here the device is here. You see this gate is under repair. And what is the control? Is the motion of this part, which is called the lip of the gate. You move it up and down. This is the control that you are going to use in order to regulate the level of the water at a desired height. So I present you the team: Brigitte d'Andrea Novel, Georges Bastin, Valérie Dos Santos, Jonathan Dehalleux, Miroslav Kristik, Luc Mons, Roemine Nguyen, Christophe Prieur, and Raphaël Vasquez. So now the modelization. We are going to use the modelization which is invented by Saint-Venant, and in this model, the velocity, the horizontal velocity of every point which is on the vertical line is, roughly speaking, the same. It's denoted V of t and x. And the age is the height of the water at time t and position x. This is the equation. The first one is the conservation of mass, and the second one is the conservation of momentum. For the moment, there is no control. Now we have the control. Yes, before there is this picture by Saint-Venant, and the key point is, in fact, on the date. You see, this is very encouraging, Carlos, because he discovered his law when he was 74. Yeah, so we keep going. Yeah. Yeah.
It's just wait 14 years. I mean.
So the control now, the picture that we saw before is this one on the right. This one, but we can also use this type of gates. And this is the U, and you want to prescribe U depending on what you observe, what you measure. And what is measured is the height of the water before the gate. So you can put it in some more general framework. This is interesting because there are many other applications. And so the equation is yt plus a of yx is equal to 0, where a of 0 is a diagonal matrix, and the entries are not 0 of this matrix, and all the eigenvalues are distinct. Now the boundary condition, what you say is that what is going inside the domain depends on what is going outside the domain. And of course, this is the G, which is part of the G is fixed, but the other part is the feedback law that we are going to choose in order to have exponential stability. So there is some other application, which I've listed here. And there is a book that I'm writing down with Georges Bastin. It's going to appear, it's always next year, yes? So we are in 2014, so next year is 2015. But maybe in January it will be 2016, yeah. So what is the stability issue? What is the stability problem? You want to find under which condition on the G, which is the feedback law, you have exponential stability in some norm, which is denoted by x. So you want to have the inequality 2 if the initial data is small enough. And what is the condition on G in order to have this? Let us start with a simple example, 1D. Yt plus lambda yx is equal to 0. Lambda is positive, for example. And so it's easy to see what is going on. The value at time t2 is just k times the value here, which is the value here. And so at the time t6, for example, you get k to the power 6, the initial data. So the condition is very simple. It's necessary and sufficient. In order to have exponential stability, you must have, and this is sufficient, that the absolute value of k is less than 1. Now we move to something which is more general. We looked for systems. So now we are in n dimension. And we assume for simplicity that all the eigenvalue, which are the speed of propagation, are positive. And then, this is linear, you can just look to the spectrum. And since we are in 1D, it is sufficient to look to the spectrum. And the condition is that if all the eigenvalues have a real negative part, then you have exponential stability, and this is necessary and sufficient. So you get this condition, which is a little difficult to check. But you have the necessary and sufficient condition in the linear case. But there is something which is very strange, and we are not familiar with this problem in finite dimension, is this effect that I'm going to explain you. We consider n equal 2, and we take lambda 1 equal 1, lambda 2 equal 2. And the matrix K is given by equation 1. And then you look to the condition. You look to the spectrum, and you get that you have exponential stability if and only if A is between -1 and 1 divided by 2. But then you do perturbation on K. No problem. If you do perturbation on K, you still have exponential stability if the perturbation is small enough. But if you do perturbation on the lambda I, then there is something which is very strange, is that you do not have robustness with respect to small perturbation on the lambda I. If you take lambda 1 and lambda 2, which are given by 1, and when n is large enough, lambda 1 is close to 1 and lambda 2 is close to 2, then you see that y2, which is given by y1, y2, which is given by 2, is a solution with the boundary condition, but we do not converge to 0. So you see, you do not have robustness with respect to the small perturbation on the lambda I, robustness of the exponential stability. So, of course, this will be a problem if you are going to study the case of nonlinear systems, because the lambda 1 and lambda 2 are going to change with the state. So now the next question is under which condition you have exponential stability, which is robust on small perturbation on the lambda I. And the result is known. You consider this number rho 0 of k, which is defined by 1, where rho of a matrix M is the spectral radius of this matrix M. So you have a new condition. And the result is that you have exponential stability, which is robust with respect to small perturbation on the lambda I, if and only if rho 0 of k is less than 1. And you see there is something which is very interesting. You have to have robustness with respect to small perturbation on the lambda I, and you get robustness with respect to all perturbation on the lambda I, because you see that the condition does not depend on the lambda I. It depends only on k. So now the natural question is that if you have rho 0 of k less than 1, do you have exponential stability for the nonlinear system? Let me first mention that for the linear system, it does not depend on the norm you consider. You consider CK or HL, Sobolev spaces, you get the same condition. An example. So we consider this matrix Ka. You compute rho 0 of k. This is the example that we gave before. And you find that you have exponential stability, which is robust with respect to small perturbation on the lambda I, if and only if A is between -1 divided by 2 and 1 divided by 2. So you see that -1 divided by 2, which was considered before, is in fact the limiting case. So this problem has been first considered in the case of in the framework of CK space, CM space, and the condition, a sufficient condition, was given by the Litassian school, and it is the following. We consider the infinity norm for X, the associated norm for the matrix K, and then you consider the infimum of the norm delta K delta M minus 1, where delta is a diagonal matrix with positive entries. And this school proves that if you have rho infinity of k, which is less than 1, then you have exponential stability for the C P norm, whatever is P, provided that it is larger than 1, at least equal to 1. So now we want to compare rho infinity of k and rho 0 of k. of course, you cannot expect to do better than rho 0 of k. So you must have rho 0 of k less or equal than rho infinity of k. And this is what you can prove. But unfortunately, the condition rho infinity of k is stronger than the condition rho 0 of k less than 1. If we go back, if we consider this matrix Ka, which is defined by 2, if you compute rho 0 of Ka, you find square root of 2 times A, and rho infinity of K, you find 2 times A. So the Litassian condition is that the absolute value of A is less than 1 divided by 2, and the condition for linear system is that the absolute value is less than 1 divided by square root of 2. So there is a gap. Now we move to the Sobolev space, and we try to find a sufficient condition for the Sobolev space, Hk, where k is at least equal to 2. And then you define this. So the 1 is just the Euclidean norm, and you consider the norm of the matrix K for this Euclidean norm. And then you do the same. You consider the infimum of the norm of delta K delta minus 1, where delta is in the set of diagonal matrix with positive entries. And you find a new number, which is rho 2 of K. And what we prove is that if you have rho 2 of G prime of 0 less than 1, then you have exponential stability, whatever is the norm in the space Hk, whatever is K, provided that it is at least equal to 2. So now we have three numbers. We have rho 0 of K, rho 2 of K, rho infinity of K. Rho infinity of K less than 1 is a sufficient condition to have exponential stability in the CM norm. Rho 2 of K less than 1 is a sufficient condition to have stability, exponential stability for the Sobolev norm. And rho 0 of K, this is for linear system. So we want to see if these sufficient conditions are they necessary. And it turns out that first, if you want to compare, rho 0 of K has to be the least one. But you can prove that rho 0 of K is equal to rho 2 of K until the dimension 5. 1, 2, 3, 4, 5. You have rho 0 of K is equal to rho 2 of K, so you have the optimal condition, because you cannot do, of course, better than the linear case. But unfortunately, if the dimension is 6 or larger, then you may have strict inequality. This is the first result. Now, if you want to compare rho 2 and rho infinity, you can find already in dimension 2 that you may have rho 0 of 2 of K is strictly less than rho infinity of K. So then the next question is that if you have rho 2 of K less than 1, do you have exponential stability for the CP norm? It's a natural question. But it turns out that the answer is no. We find an example already in dimension 2, where we have rho 0 of K, which is equal to rho 2 of K, because we are in dimension 2, less than 1. So we have exponential stability for the Hk norm, whatever is K, which is, if it is larger than 2, at least equal to 2. But you do not have exponential stability for every Cm, whatever is M, with M at least equal to 1. So this is a little surprising. I would like to give briefly some idea of the proof. More precisely, I would like to explain why rho 0 of K is not sufficient, maybe not sufficient, and is not sufficient for the exponential stability for the Cm norm, for example, for the C1 norm. You see, rho 0 of K less than 1 was stated in order to have exponential stability with respect to small perturbation on the lambda I. So you may have expected that it's okay for C1. But the problem is that you require that you have robustness with respect to small perturbation, but which are constant in time. And this is the difference. Because if you want to make it with C1, of course, the perturbation due to the nonlinearity will not be constant with respect to time. And this is why rho 0 of K is not sufficient for the exponential stability, for example, for the C1 norm. So I briefly describe why. So this is a matrix A of y. And so you see the only thing which is not linear is 1 divided by R2 plus Y2. The other things are linear, even the boundary condition. So we have some condition on R1 and R2, which is given by 3, and the matrix K is given by 4. But you have some very special condition on you see there is some number psi and eta, and they have to be such that if you have a rational polynomials which vanishes on these two numbers, then the polynomial has to be equal to 0. So you see this is very special in some sense. So you compute rho 0 of k and rho 2 of k. They are very close to 1 divided by square root of 2, so we are very far from 1. And rho infinity of k is a little larger than 1. And the key point is here. This is on this slide. You see, you follow the characteristics. So when this is a color blue, this is with the slope lambda 2. When this is red, dashed red, this is the slope lambda 1. And the key point is here. The key point is that these two numbers, which would have been equal, they would have been equal in the case where you have a perturbation on the speed of propagation which does not depend on time. But now they are different. T12 and T21 may be different. So you can impose on these two different numbers different derivative of the function. This is why you obtain this strange phenomena that, in fact, it depends a lot on the norm that you consider, the exponential stability, even if you have something which is very smooth. Let me give very briefly some idea of the proof. So the H2 norm, you consider this Lyapunov function, where Q, R, and S are symmetric positive definite matrices satisfying this type of bound of commutation. They are classical in the study of hyperbolic equation without boundary condition. And then you compute V dot, and you get this estimate, and with that, you get indeed that you have exponential stability, provided that rho 2 of k is less than 1. You can also produce a Lyapunov approach in the case of the C1 norm. This is given here. So you require the condition 1. You diagonal the matrix A of y. You consider this matrix delta such that the norm delta k delta minus 1 infinity is less than 1. We know it exists because this is the condition rho infinity of k less than 1. And the Lyapunov function is given here. You take the sum of V0 and V1, where V0 and V1 are defined here. So you see the expression is a little complicated, but again, you can find that you have a Lyapunov function for the system, and so you get the exponential stability for this C1 norm by using just simple Lyapunov function. Okay, I'm going to stop here, and thank you very much for your attention, and happy birthday, Carlos. No, the movie, it's not me. The movie was done by, the guy was, in fact, I don't know him. It's a recent movie, even if it is in black and white. And you see, now it's very fancy to do a black and white movie. And if you look to the movie, sometimes there is a little color, maybe a little, but very little. At some point, you can see some, during the 2 hours movie, there is maybe 25 pictures. So you have to be very, you cannot sleep for sure. If you will miss it.
Black and white.
Black and
What?
black and white, yes, very good. No, but this is very interesting because it shows that this is a fiction. So it does not appear really in real life, but it's important to see that even in fiction, people see that it is very important to have a regulation.
In this general system of type yt plus a of y,
Yes, it's general system.
There also some questions about controllability, general.
Yeah, for controllability in the framework, if you have, for example, the control on both sides, but there is also result by when you have only on one side, you can prove this is the result due to Litatienne and Bopengrao. They saw that if the time is large enough and the time they give is optimal, then you have in fact controllability of the system. But controllability is not always connected to stabilization. So I present only the stabilization part. But you're right, the controllability is known, yes.
Yes. Can you generalize your approach to the case where the matrix A is replaced by an unbounded operator, or the case of
no, not so clear. No, this is very special to this type of systems. Yeah. No, it's not completely. You see, the Lyapunov function is rather simple, and if you have something which is more complicated, I think this type of Lyapunov function will not work. Yeah. Yeah.
How do you get these things that what you call row 0 and row 2 are equal up to dimension 5?
But you see, you start with 1. This is 1 was working. You start with 2. First, you try to find a counterexample. This is the first attempt. But no counterexample, so you try to prove this is true. And then you keep going. And then at the end, you arrive to dimension 6. And then there is a counterexample.
Is it something algebraic?
It's not very clear for me. No, it's a little surprising, in fact. Yeah. In fact, in the case of the river, you see, there is this pools. The number of pools is 7. Okay, so you may say the dimension then is 14. So maybe it is not working. But it has a special structure. This is 2 by 2 diagonal, and then in this case you still have row 0 of k is equal to row 2 of k, even if the dimension is 14.
All right, and next speaker is Annie Raoult from Universidad, and she'll be talking to us about angular energies in lattices.
Thank you. Thank you. So first of all, of course, thank you to the organizers and the scientific committee. So I will first start with some memory. So if I remember correctly, you arrived, Carlos, at the Laboratoire d'analyse numérique for an internship under the joint supervision of Fulbert Mignot and Jean-Pierre Puel.
Yes.
Okay, so you met them and they gave you a very difficult problem to solve. And a week later, at coffee time, Fulbert and Jean-Pierre were, in a way, disappointed and in a way very happy, because in a matter of a week, you solved the problem they gave you for 4 months. And they had to find some new idea. Do you remember that? So, and of course the story goes on. Well, so I will talk about angular energies in lattices, or more generally of finding equivalent laws for lattices. This is a subject I have been working from time to time during the past years, and this conference was a very good impetus to force Hervé Ledray and I to go on and try to solve the points that resisted. So this introduction is very simple. All of you know that it's important to find equivalent laws, equivalent energies for structures, and in particular for lattices. And let me go back to the previous slide. You can see that graphenes are very fashionable those days. These are covers of CNRS magazine, and a year with CNRS from last summer. So I do not pretend we are going to deal with the electronic properties or other properties of graphenes, only with aspects in crystals that are similar to aspects in mechanical structures. Okay, so I just want to emphasize the fact that in the literature you can find recipes for deriving energies for lattices, and there is the Cauchy-Born rule, which is stated in several papers. And for instance, for hexagons, there is an infimum somewhere in the formula. So I will not discuss this, but just remember that we could find an infimum with respect to a vector in R3 somewhere. So the question is, can we obtain energies for lattices by rigorous methods? Many researchers have been working on the subject for years, and I mentioned some of them here. Of course, there are other ones. Okay, so let us begin with a very simple example, square lattices, and let us still make it simpler. Let us first concentrate on interactions that are only two-point interactions. The energy of the lattice only depends on the length between neighboring nodes. And the energy will change when the length change. So the energy is written here. The energy is a sum of the energy due to the new position of the nodes, the new lengths of the bars, and the total energy is a sum with sum of terms that only involve the length of the deformed bars. So psi of bk is shorthand for the length of any bar. A bar may be either horizontal, so this one is with, I guess, obvious notations. If the deformation, this is a deformation of an horizontal bar by a deformation psi, and here are the vertical bars, and you sum all of them with the power 2. At the very beginning, the deformation is defined on the nodes. Of course, this is a discrete deformation. You want to obtain, let us go a little bit quicker. You want to obtain a convergence result, and you will plug everything, of course, in a continuous setting, which will be the following. You replace, everybody would do that, you replace the discrete deformation that is defined at the nodes by a piecewise affine interpolate at the nodes. And this is quite easy. This is well known. This has been done by Bidas and co-authors many years ago. You are lucky because the discrete energy immediately rereads in an integral form. This equality is exactly an equality with an internal energy easy to write. So psi now is a function defined on a subset of R2 that goes into R3. The gradient is a matrix 3 by 2 with columns U and V. Okay, and it is very easy to prove that these energies gamma converge to an energy which has a structure quite similar to the problem you start with. The only change is in the mathematical treatment. The energy here, the starting energy here is just replaced by its quasi-convexification, its quasi-convex envelope. And in this very simple case, you can compute the quasi-convex envelope. You just have to replace both terms here by their positive part, then squared. Okay, so this is very well known, very ancient. You want to take into account angular energy. So for squares, it's still easy enough. What new terms should you take into account? So the new energy is composed of two terms. First, first the energy due to the bars we had before, which is here, and now I want to add some moments. MKL will be will take into account the change of the angle between bars BK and BL. And a way of doing this is to take the inner product. So this inner product is 0 when the angle is equal to pi over 2, which is an example, a particular case that we can take for square lattices with pi over 2 angles at rest. Okay, so there is just a little trick here, which comes from the fact that the piecewise affine interpolation, which we chose just as a tool before, will allow us to deal with the angles that are here or there, but not with those ones. Because just the affine interpolation that I defined can't translate this in an integral. So we introduce an alternate triangulation, and working on both of them, we are able to rewrite exactly the discrete energy in an integral form, and it's not too difficult to obtain the gamma convergence result with the quasi-convexification step that, of course, was expected. Okay, there is just some technicality in the fact that both affine spaces that I am considering now are not the affine spaces I had before, but I put here a star. It's like R star are the numbers in R which are not 0. Now the star means that 2 points here should not be mapped on a single point. Otherwise, I can't divide. Suppose that 2 neighboring points come on a single point, then I can't divide by 0. And this is just a technicality. We obtain an equivalent energy, and in a way, we can say that we prove that in this particular case, the Cauchy-Born rule for square lattices that you can find in the literature is nearly is good. Of course, Cauchy-Born in the engineering literature misses the quasi-convexification step, but this is quite normal. Okay. How much time do we have still? I still have 20 minutes? No. 10, okay. 10. Okay, so, thank you. So, this was easy enough to obtain, and I want to stress the fact that this result was did not involve any homogenization step because of some natural compatibility conditions that are valid here taking rest angles equal everywhere in each angle. The rest angles I chose are pi over 2, and this allowed this very simple formula. Suppose we can extend this to rest angles that are different, and under some natural or not natural compatibility conditions, the energy obtained is still very simple. If some compatibility conditions are not true, then there should be some homogenization. And now I turn to the second part of the talk, and we will see that for hexagons, we can't avoid the homogenization step. So the plan is the same one. First, only length, and I hope to get some time for the new part where we take into account the moments. Hexagons are more complicated to describe. They are called complex lattices. All nodes are physically equivalent, but for the mathematical description, it's easier to separate nodes into type 1 nodes that are black on the picture and type 2 nodes that are white. And in the first part, I will consider that the basis cell is the parallelogram Y here, which consists of a full triangle TF and an empty triangle TE. In the full triangle TF, I have all 3 bars. I have 3 bars. And if I repeat this in this direction S, this will be S. And if I translate it also in this direction T, then I can recover the whole of the structure. We first consider energies that only incorporate changes of the length, which is written here. So I slightly change the notation because the letter psi will have a slightly different meaning here. Before I had psi defined at nodes and the same notations for piecewise affine functions that interpolate psi. Here, now, the discrete deformation is chi, defined at the nodes, and I will associate with chi 2 functions, a piecewise affine function psi, which is equal to chi at nodes 1, and another one. So let us first concentrate on the energy. The energy is due to the discrete deformation, and it takes into account the new length of all bars. Now, these bars are not in directions S and direction T, but I can express any bar by a vector is the sum of 2 other vectors as a sum of something which goes this way. For instance, this bar, which will be bar 1, is different position in the sum of the different position of this one and of that one, or the different. Okay, so I introduce psi, which is piecewise affine. I introduce psi, which is piecewise affine at nodes 1, and I introduce a constant function gamma, which takes into account the deviation between a node 2 and a node 1, which is, let's say, the foot of 1. So this is 2, this is the foot 1 of 1, this is gamma, and now all bars, all 3 bars here can be expressed as sums or differences of the derivatives with respect to S and T of the affine function and of the discrepancy gamma. Okay, so it's just an easy computation to transform the discrete energy into another energy, which is a continuous energy defined on the sheet the lattice lies on, and which is here. And this energy is made of 3 terms. Each term corresponds to the change of length of a bar. And for instance, this one, it corresponds to gamma, the discrepancy between the new top node 1 and the new node 1, 2 and the new node 1, and this one corresponds to derivative with respect to S minus gamma, etc. And the energy is not homogeneous because on what corresponds to full triangles, it's given by that, and on the empty triangle, it's 0. But this is not a problem. It could be a problem. In fact, it's not a problem. Let me recall you that all bars are in a full triangle. Okay, so we can prove a GABA convergence result again, and we obtain that the limit energy is given by an homogenization process. What would have been better? It would have been to avoid the homogenization, but it does not work. It's not true. It's not that it doesn't work. It's not true. Well, what was satisfactory is that there is, in defining the gamma limit, there is a first step. You first introduce a function W naught, which involves exactly the same infimum with respect to a vector tau in R3. The infimum I showed you at the very beginning, and you find this formula in the literature. Okay, so this is in a way satisfactory, and then you homogenize. So we can say that the heuristic Cauchy-Born rule is still visible in the formula, but maybe because we are looking for it. And it does not resist taking angles into account. Now, in the very recent weeks, maybe because of this conference, Hervé and I came back to a problem we had not been able to solve 2 years ago, and we changed the procedure. So now we want to take into account the total energy of the hexagons, and we have the change of lengths, we have the angles at rest at 2 pi over 3, and the energy due to the angles will, as a consequence, be written this way. And also, we introduced a Lennard-Jones term, which is better for preventing points of arriving on a single point in R3 than the very violent condition I had put before. The approach we used when there were no angles was in a way close to the reasoning by Stefan Müller many years ago, but it doesn't work here because there is a density argument that has to be used somewhere, and it can't here because the energies don't have the Lipschitz property that makes the density argument work. So we came to the Italian literature, which is, of course, well known, but that we are not so used to. Well, we had not practiced it in a way. And there are many works by Brides, Alicandro, Cicalese, and handbooks by Brides, explaining how to use the theorem by Butazzo. And so this is a totally different approach. You first prove that your limit energy can be written under as an integral of a function that only depends on the gradient of the limit deformation. And once you know that, in order to identify W, so you first prove that the identity energy will write this way. And when you know that, you can identify W on looking only at piecewise affine functions. So it works. So you have to incorporate in a way a Butazzo theorem, which is Butazzo theorem is seems simple to read, but when you want to prove that something is a restriction of a Borel measure I don't want to go over my time, so maybe I still have time, 2 minutes or? Okay, so at the very end, we want to prove that I am given a domain omega, and I want to prove that a limit energy will write integral over omega of W of gradient of psi of x, and I want to know what W is. But you have to put heavy machinery, you have to use a heavy machinery and first localize. That is to say, you can't work only on omega, but you have to define energies on subsets U of omega, prove that this function of a pair, psi function and U, an open subset of omega, satisfies some properties. Then for any U, I of psi and U can be written as the integral of U of W of gradient of psi and x dx. And you have to define this correctly. So this is done here. We introduce U subsets of omega. I define energies of U by taking into account only bars and triangles that are included in omega. Again, I have to use an alternate triangulations because angles it's tricky because angles belong either to the first Delaunay triangulation or to the second Delaunay triangulation. Try to forget some parts of the Lennard-Jones energy that could go to infinity. So we have to prove that we can change the deformations without changing much the energy, but with bars that are not too small, etc., etc. At the very end, we finally apply Butazzos theorem, and we are sure that we have an energy that reads this form. And afterwards, there is also a sort of trick how to obtain W. Well, W for a given matrix or a given linear transformation is necessarily reads this way necessarily because by the very method we know that this function W is quasi-convex, and it is the minimum of the energy because it has been defined this way. Then it is the limit of some infimums, and you can rewrite the energy. Well, it's tricky, it's lengthy, but at the very end, you obtain that the W that exists coincide, which was usually called the homogenized density, being defined by this formula where you have to take the infimum over increasing domains, take the mean value, and then minimize. Okay, so at the end, maybe it was much work for something which will not be very helpful for practical life, because calculating this infimum, which is nearly the problem you start with, is maybe as difficult as to solve numerically the discrete problem of the lattice. Okay, thank you for attention.
Thank you. Are there any questions? Okay. Any further questions? If not, let's thank Annie again.
First of all, I want to thank the scientific committee and the organizing committee for the great job they did. I mean, for the organizing committee, because I found the organization wonderful. The place they found is wonderful. So thanks a lot for that job, and thanks to the scientific committee for the invitation. I'm deeply honored to be here, to have the opportunity to speak at this conference in your honor, Carlos. We only met recently. I think it's 3 years ago. I knew your papers, so I knew how a deep mathematician you are. But I wasn't aware of your main quality, your kindness. So thanks a lot, Carlos, for being like you are. So now let me talk about the scientific part of my presentation. Our motivation is this joint work with Helmut Albrecht from the University of Basel in Switzerland and Benedict Puig, my wife in Po, is to do shape optimization in a context where the device that you have designed will be manufactured. And if it is manufactured, you know that you will never reach the optimal designs that you have planned to build, because you will use a manufacturing tool. So there will be some tolerance inside the design that should be taken into account. So if you have planned to do a piece like that with straight planes, once it's manufactured, it's something like this. And engineers know that, and usually when they make the conceptions of a device, they add here a plus or minus, plus some length, which is the tolerance of fabrication, which is the tolerance of use. And my objective is to take this uncertainty into account for an optimization. That will be a long step objective. And in this presentation, I will explain how one can take this into account in order to make numerical computation of the physical relevant quantity of interest for engineers. So you can think of compliance if you are working in civil engineering. You can think about some modes if you are working in vibration. You can think about the drag if you are working in fluid mechanics. Another reason to incorporate this uncertainty in the computation is something that here you can't see, I guess. On my laptop, it's perfectly visible. It's just about what you have in your cars. You have tires and you have brakes. On tires and brakes, there are some weakness points. When you see them, you can use your device. When you don't see them, it's too used, it's out of tolerancy, and you have to change them. And obviously, you will use your tires, you will use your brakes, and their shape will be modified, and their properties will be modified during the lifetime of use. So that's our motivation. So now let me explain a bit the mathematical modeling of this. The modeling we have chosen for that. Our idea is, since we are looking only at small perturbation of nominal boundaries, we can represent them as graph over the nominal boundary. Obviously, there is a small parameter, epsilon, which represents the characteristic size of the tolerancy, the plus or minus 0.5 with respect to the 20 in the former example. So this is a small parameter. And if you think about the shape of your brakes or the shape of your tires in your car, you don't know that. There is some randomness in that. So there should be some random parameter, small omega, here in the description of your ice with respect to the nominal boundary. So this is our model. We want to discuss how one can take into account such geometrical randomness in the domains where we want, where the device we want to use is built. And since it is random, the PDE that is inside has random coefficient, and its solution is also random, and the quantity of physical interest, which is a scalar quantity computed from the solution of the PDE, is also random. So our objective is the following. So I will assume a lot of things at the beginning. I will assume that I have a complete probabilistic description of my geometry as a graph. So I know the random process giving me the ice with respect to the nominal one. And I want to compute as much information as I can on my output. So let me start with experimental mathematics. Now we can use a code and see what will be the results before doing mathematics. So I will take a purely academic example. My reference domain is a unit disk, and I perturb it by modifying its polar representation. I add the first Fourier modes, and I perturb them with random coefficient, taking a uniform distribution on this interval. And so there are some here with different realization of the random shapes. Here for epsilon, which is 1/8, and here epsilon is 1/4. So you have more distant random shapes than for the previous epsilon, which is the half of the first one. And as a model quantity of interest, I just take the Dirichlet energies, so the energy of the solution of the simplest equation we can think of, that is minus Laplacian equals 1 in H10 of the domain. And, well, now we can make a lot of computation of this type. So each point you see is the resulting quantity from a sample. So for each point, I just make 2, in that case for the black, I can't read. I think it's, for the black, it's 300 realization, and for the red one, it's 3,000th equalization. And here you have what are the first moments with respect to epsilon, the size of the amplitude of the admissible perturbation. And what we see on this picture is, from this very naive point of view, we see that there is some very simple law in terms of epsilon that allows us to describe the behavior of this average quantity of interest. So that's the precise questions that we will that I want to explain now to you, how to do that. We want to prove first that there is some power expansion of the moment of the output law with respect to epsilon, that this power law has deterministic coefficient, and that, more importantly, that I can compute very easily, from a numerical point of view, this coefficient. Okay, so forgot the randomness for a while. We have two domains which are close one to the other. In order to describe how our quantity of interest varies from one domain to the other one, there is a wonderful tool in the toolbox of shape optimization, which is the shape calculus. And the most useful formalism for that is the one introduced by Murat and Simon some time ago. I remember the date because I was born on the date of that year. Of the famous unpublished preprint of the Laboratoire d'analyse numérique. So the idea is to parameterize your deformation with diffeomorphism. And diffeomorphism, which are perturbation of the identity here in a very nice space, which is a boundary space. So we have a real calculus, shape differentiable calculus on this set. And the idea is to define our quantity of interest through this composition here. And now this is a function not of a shape, which lives in it does not live in a vector space, but which acts on diffeomorphism, and that's something we can differentiate. And you can do that, at least at any order. So I will restrict myself to the second order. And at second order, if you deal with normal perturbation, you have this very nice and very simple Taylor formula. So you have here the shape gradient, and here the shape Asian that acts on the normal component of our field. Obviously, I guess that in the audience, everyone is familiar with shape gradient. I don't think that everyone is familiar with shape Asian. So let me recall you the most important results to my point of view about this object is their structure. The structure of shape gradient is known from a very long time. I think it's Adamar that for the first time realized that when you deform a body so imagine you have a body and you perturb it with a deformation speed. If your deformation speed is purely tangential to your body, then the body is sliding on itself. If you see it as a set, the perturbation will appear only at the second order in time. So the first derivative of any quantity of interest should not depend on the tangential component. It should depend only on the normal component. So this theorem expresses the fact that the shape gradient is a linear continuous form acting on scalar function on the boundary, but those scalar functions are the normal component of the vectorial deformation field. For the shape Asian, it's not true anymore, since the domain itself at time t is perturbed by another two term. When you make the quadratic approximation of any functional, you should see this sliding. So you should see the importance of tangential component. So this second part of the theorem is much more recent. I think it's around the year 2000. It was written by Michel Pierre and Ariane Novruzi. And it tells you that the shape Hessian, the second derivative, is the sum of two terms. The first one is B, a bilinear form, which acts on function, scalar function on the boundary, or the moving boundary, on the unknown boundary. Those two terms are just the normal component of our vectorial deformations. And you have the shape gradient that acts on something which mixes the tangential component of the two fields. You have here the second fundamental form of the solution, of the domain that appears. So it's a rather complicated coupling of tangential components. However, I've chosen, I wanted to, before entering in the details of the following ideas, I wanted to show you an example. The example for what are the derivatives in the example, in the academic example I've chosen to treat here in this presentation. It's rather well known that L is something simple. You just solve your Laplace equation in your domain, and the shape gradient is just have to integrate your deformation fields, its normal component, against the square of the gradient. You have the same that appears in elasticity equation if you work with the compliance, similar effects for the drag in fluid mechanics. But the shape Hessian is a bit more complicated, since if you have this nice guy which is just of the same type as the previous one, so you integrate the square of your normal deformation against something that depends on your solution and on the geometry. You have this term which is much more complicated. It's a Dirichlet to Neumann map that acts on the products of your deformation fields with the normal derivative of your solution. So if I want to compute explicitly this quantity, I won't keep this expression. I will just integrate by parts, and I will write this as a volume integral, the volume integral of the square of the gradient of the harmonic extension of my boundary condition of this guy. So this is something that I can compute. And if one wants to really understand those quadratic forms, I push the example to the end. I choose my domain to be the unit ball so that I can use spherical harmonic expansions and solve everything explicitly and compute explicitly what is this B. And this B is just this. And you see here you have the K that corresponds to this Dirichlet to Neumann map. K is the principal symbol of the Dirichlet to Neumann mapping, usually. So, now our idea. Our idea is very stupid. I must confess, I'm a bit ashamed. The idea is we have a random process, but for each representation, or almost each representation of the process, we have a Taylor formula, which is uniformly valid. And then we just have to integrate. And in order to ensure that we can do that, we have to make some assumption on the random process, X. So X should be integrable with some moment in some space of function, scalar space of function acting on the boundary. So here, don't be afraid, C21 is just in order to fit the structure theorem that I have quoted before. It's not mandatory to have as much regularity. You don't need that for the examples that I have shown, the practical example. It's just to have a general writing. And the other one is, so I wrote it in a very strong way. Since you are describing graphs, you know that you can write graphs over a nominal domain only on a tubular neighborhood of the original domain. There is some problem of injectivity of the normals, so they cannot cut each other, so it's called the cut locus. This is the maximal size of the tubular neighborhood around a regular surface where you have local coordinates. So this is this reason, that for that reason, I require that the process is uniformly bounded. uniformly in the random coefficient. So it prohibits me the use of Gaussian process, for example. So when I have that, I can write event by event my Taylor formula, and I can integrate it. And if I integrate it, it's elementary calculus. This is what I get. The expectation of my quantity of interest is just the quantity of interest evaluated on my nominal domain plus a first order term plus a second order term, and those order terms are just coming from the integration of the previous formula. You have the same for the variance with a bit more complicated formula, but this is what life is about. And you can have that for any higher order, moment as soon as you assume enough integrability of your process in terms of omega. So you have to assume that it has enough moment, essentially. Now, well, if I want to make numerical computation now, to compute these coefficients, I have to compute term of that type, expectation of the shape gradient applied to my random film, or expectation of the bilinear, the shape Asian applied to the random fields twice. So let us compute this term. I assume that my process is centered to simplify things. And the first term in the variance is the following. I have to compute the expectation of the square of my gradient. If my gradient is as I have, the one I have shown, it has a kernel, it has a which I call small l, and then I can expand this, and by Fubini's theorem, I just this simple guy. And when I see that, I say, okay, I just need the 2 points correlation of my process to compute this. But how can I deal with more complicated terms, the ones that involve the Dirichlet to Neumann map? I won't be able to do that. So when I look at this, I see that here appears the integral operator associated to the covariance. And I know a spectral basis for that. This is Kaunen-Love basis. So we have immediately the idea of decomposing our process on the Kaunen-Love basis. So basically, it will provide me a basis, two bases, a basis of spatial function and a basis of flows associated to those guys. So roughly speaking, I will have a separation of variable miracle that appears if I do this decomposition. My process will be as an infinite sum of a random variable times a spatial function. So random variable and spatial variable are fully separated. And now if I put a technical assumption here that is not important. I have two commands to do. If I use really Kaunen-Love expansion, first, I don't know that my randoms variables are independent. I just know that they are uncorrelated except in the Gaussian case. And then I get that those functions are orthogonal in L2 and lives in L2. For L2 function, I cannot apply my model. And for technical reason, practical reason, to have simple expression before, I will assume that my random terms are independent. So it's not Kaunen-Love what I will use. It's a different model inspired by Kaunen-Love expansion. When I do that, now it's simple, it's trivial computation. You just have to use Lebesgue, do that for a finite number of terms. You compute your expectation, you separate what depends on the spatial variable of what depends on the random variable, and you immediately get that. The convergence here is just obtained by Lebesgue's convergence theorem. And you have also a nice expression for the variance. And I claim this is useful for numerical computation. So it suffices to evaluate the coefficient of my polynomial expansion, second order or third order expansion of the expectation or of the variance, to evaluate what is the gradient in the direction phi I, and what is the Asian evaluated in phi I. So remember the expression in the case of the Dirichlet energy. the gradient evaluating phi I is just the integral of phi I against something that I have already computed. So it's just a numerical quadrature. For the Asian, I use the expression with the integral as a volume integral representation. So in order to compute this, I just have to solve this additional PD, this additional boundary value problem. But it's always a Laplacian. It's always on the same domain, on the nominal domain, and just change the Dirichlet boundary condition. For general,
It's on D naught?
yeah, it should be D naught, sorry. It's a nominal one. I just have a single mesh, a single domain. And yes, so in that case, it costs to me exactly n+1 resolution of the PD, which is ridiculous with respect to the cost of a Monte Carlo method in order to evaluate that. Of course, for more general objective, I will have to use adjoint. Here I am in the case where the adjoint, in order to evaluate the derivative, to evaluate the gradient, I will introduce the adjoint state. Here I am in the case where the adjoint is the solution itself. So I have a miracle here. But in the worst case, it will cost me a factor 3 here. So, and let me see what are the results of this computation on my academic example. Here you have the cloud of points obtained by Monte Carlo. And in red, you have the line, which is the polynomial that I have computed. And you see, in that case, it fits perfectly. So here I have taken, for the distribution of alpha is uniform law, here I've taken the beta law, which is non-symmetric. And if you remember in our results, you had an expectation of A alpha to the power of 3 that cancel in the case of a symmetric law. So the approximation is better for the uniform, for the variance in the case of the uniform law than in the beta law, and that's something that you can observe here. So I do not claim that this is a very satisfactory result, because if you try to do that for eigenvalue problems, you will see that the range of epsilon for which you have such a nice agreement is much more small. No matter. We are doing asymptotic analysis. The range where the asymptotic regime is reached depends on the problems. There is no contradiction. But it allows you, for small tolerances, to have an efficient way to compute the characteristics of the output law. And this is the first steps if you want to have an optimization condition and an optimization loop afterwards. Okay, thank you for your attention. And happy birthday again, Carlos.
Can I have some questions?
If you push the asymptotic expansion, let's say, for the expectation up to fourth order, because the third order term will cancel probably if you have
It's purely a question about development limited expansion. And you just have to, as far as I remember, I will need a third order term in my starting initial Taylor formula. So I should, yeah. Here, you want to have the next term. Yes. Then the next term will be the expectation of the third order shape derivative applied to the field itself, 3 times. And that's something that I don't want to compute. Because, so that was
that's easier in parametric optimization.
Yeah. If I have, if the randomness will be on the right-hand side of a loading, it will be different, yes.
Some other questions?
First of all, I would like to thank to the scientific committee and the organizer for inviting me to speak today. It is a great honor for me to speak in the 60th anniversary of Professor Carlos Conca, who was my PhD advisor. Thank you. I'm going to speak about Barnett coefficients and laminates, which are joint works with Professor Carlos Conca, with Jorge San Martin from University of Chile, and Muthusamy Vaninatham from Tata Institute of Fundamental Research, which is also present here. My talk is divided into 3 parts. I will start with a brief introduction, where I will set the problem that we are interested in. In order to describe the Barnett coefficient, to define the Barnett coefficient, I'm going to introduce the block waves associated with our problem, and I will finish this first part with some references, just a few references on the topic. In the second part, I will focus on bounds concerning the Barnett coefficient. I will set the general questions that we made, and I will give the main results in laminated structures and also in the one-dimensional case. And I will finish with some open problems. Let me start with setting of the problems. We are going to consider, first of all, we consider omega to be the entire Rn, which I represented here by this bicolor rectangle. In this type of domain, we consider the classical homogenization problem associated with the divergence type operator, associated with this alpha epsilon, which will be considered to be an epsilon y periodic matrix, which is the conductivity. And this matrix, which takes only 2 values, alpha 0 and alpha 1. Alpha 0 multiplied by the identity matrix, alpha 1 multiplied by the identity matrix. In other words, in the periodic media, we are going to consider only those structures which takes these 2 values, alpha 0 and alpha 1. What we are going to do, we are going to study some properties concerning the Barnett coefficient associated with this homogenization problem, and we are taking, as the small parameter epsilon goes to 0. As usual in homogenization theory, we rescale the problem, and we denote y with x over epsilon. Y belongs to the reference cell, capital Y, that we consider here 0 to pi. The conductivity matrix alpha epsilon, the epsilon y periodic conductivity matrix alpha epsilon, will be defined using this matrix alpha. Alpha epsilon will be alpha of x over epsilon, and this matrix alpha will be defined as follows. Let's fix gamma in 0, 1. And we are going to consider all measurable subsets T of the reference cell Y such that the measure of T is preserved, such that the measure of T is gamma times the measure of Y. There are plenty of configuration. There are many possibilities. We are going to consider all structure or subsets T satisfying this property, preserving the volume proportion gamma. We define our conductivity matrix alpha as follows. Alpha, inside of this kind of structures T, will be equal to alpha 1, and outside of T will be equal to alpha 0. In this movie, we can see that there are many configurations, always preserving the volume proportion gamma. The measure of the red material inside of the yellow material will be always equal to gamma. Let me also introduce the rescaled operator, the divergence type operator associated with the Y periodic matrix alpha that I previously defined. It is well known in homogenization theory that if good properties are fulfilled, then the weak limit, the H1 weak limit of the solution of our homogenization problem satisfy or is solution of the classical homogenized problem associated with the homogenized coefficient denoted by Q, the matrix Q. The homogenized matrix Q, there are many methods in literature describing or characterizing the homogenized matrix Q. And one of them is the block waves method. And it is known that in the one-dimensional case, this homogenized coefficient Q does not depend on the microstructure, depends only on the volume proportion gamma. Nevertheless, in higher dimension, Q does depend on microstructure. And a celebrated theorem of Tartar and Murat and Tartar in 85, proved that Q lies in a non-trivial set when the microstructure varies, preserving the volume proportion gamma. What we are going to do? We are going to introduce a new coefficient, which is the Barnett coefficient associated with this homogenization problem. And the question that appear are the following. This new coefficient is D, denoted by D, and is the Barnett coefficient. And the question that that arises arises were the following. Does this coefficient depend on the microstructure in any dimension, even in the one-dimensional case? And the answer is yes. D depends on the microstructure, which is not the case of Q. Q depends, but in higher dimension. D depends on the microstructure even in the one-dimensional case. So we are looking for the set where this coefficient lies when the microstructure vary, preserving the volume proportion gamma. In order to define the Barnett coefficient, let me introduce the block waves associated with our problem. The block waves are nothing else than eigenvectors and eigenvalue associated with the divergence type operator, and which satisfy, the eigenvectors satisfy a general periodicity condition, which is called eta y periodicity condition, given through this identity. It's not difficult to convince us that functions that satisfy this general periodicity condition are product between plane waves and y periodic function. With this change of variable, our previous, this spectral problem has a new form, is a similar form but associated with a new operator, is a divergence type operated but shifted operator, A of eta, defined in this, the last line of this slide. This spectral problem admits a sequence of finite multiplicity eigenvalues whose eigenvectors form, whose associated eigenvectors form an orthogonal basis in L2 periodic of Y. Let us now define the block waves of our epsilon scale problem, lambda m epsilon and phi m epsilon, which are by homotopy defined through these two identities, are related to the block waves of our problem lambda m and phi m previously introduced. In the homogenization process, one important matter is the first block eigenvalue lambda 1 epsilon. This is an analytic function around 0. Lambda 1 epsilon is epsilon power minus 2 lambda 1 of eta. This lambda 1 of eta is analytic around 0, and one can expand, one can use a Taylor expansion around 0 of this first block eigenvalue, which I wrote here. And let us observe that in this expansion, in this Taylor expansion, the first non-zero term is the second derivative of lambda 1, evaluated at 0. Of course, multiplied by psi L, psi k, psi L. When we take epsilon goes to 0, this first term is alone important. And this second derivative, multiplied by 1 over 2, is exactly the homogenized, coefficient, QKL. But if we work with plane waves such that the plane wave wave number psi power 2, epsilon power 2 is a big order of 1, then the second non-zero term in this expansion also needs to be considered as epsilon goes to 0. So this is what we call the fourth derivative of lambda 1, evaluated at 0. We call D, dKLMN, and is our Barnett coefficient, which is a tensor, and we denote by D. Let's now characterize Q of eta, the homogenized quantity Q of eta, which is a quadratic form, QKL eta K eta L, through this integral form in terms of a self function x1, which is solution of this partial differential equation. In the same way, one can characterize the dispersion, Barnett quantity or dispersion quantity D of eta, which is dk Lmn eta k eta L eta m eta n, has this form, is an integral form in terms of another self-function x2, which is solution of this differential equation. And let us observe that in this differential equation, the right-hand side also appear, in the right-hand side appear the previous self-function x1, which define the homogenized quantity q of eta. I will finish this first part with some references, just few references about block waves in homogenization. I just write here 3 references: the book of Ben Susan Lyons and Papa Nicolau, the paper of Conca, Vaninathan, and Ganesh and Vaninathan. And concerning bounds and Barnett coefficients, the paper of Murant and Tartar, which I have already cited, where bounds on homogenized coefficient in higher dimension are done. Paper of Conca, Orive, and Vaninathan, where the definition of the dispersion or Barnett coefficient is given. And our paper, where properties on this coefficient in a low contrast regime is studied. Let me now start the second part of my talk, where we are looking for the variation of the dispersion coefficient, or the Barnett coefficient in laminated structure and one-dimensional case. Since let's first fix gamma in 0, 1 and eta in the dual reference cell -1/2, 1/2, and we consider all measurable subsets T such that, included in subsets of Y, such that the measure of T is preserved. The measure of T is gamma times the measure of Y. For each microstructure T, there exists a dispersion or Barnett coefficient d of eta, which is a negative term, is minus the average of alpha gradient of the cell function x2 gradient of x2. The question that we ask are the following. Is the set of the dispersion of the Barnett coefficient a bounded set when the microstructure vary preserving the volume proportion gamma? If the answer of this question is yes, there exist microstructures where the maximum and the minimum of this set are attained, or in other words, there exists the best and the worst microstructure. And we try to answer to this question in the case of laminated structure. A laminated structure is a structure where the conductivity is depending only on one direction, and without loss of generality, we consider that our conductivity depends only on first direction y1. With this hypothesis, our cell function x1 and x2 are also depending only on the first direction y1. One could integrate the equation that solves x1 and x2 and could find the homogenized quantity q of eta and d of eta, which has this form. We have these 2 forms, where in the dispersion there appear a function at, a function which depends on the microstructure, and this dependence is through the characteristic function. Let me recall the definition of d of eta, the quantity, the Barnett coefficient d of eta, and let us observe that first of all is a negative term, and is a multiplicative. There are 2 multiplicative terms. The first term, which I denote here by term 1, is a term which depends only on the dimension of space and on alpha 1, alpha 0, and also about the average of 1 over alpha. Is not depending on the microstructure, is depending only on the dimension of space. The second multiplicative term, which I call here term 2, is the dependence on the microstructure of this Barnett coefficient is through this second multiplicative term, and this dependence is through the function at, which depends on the microstructure through the characteristic function, chi t. If we consider the one-dimensional case, or if we take this formula for the case n equal to 1 and also eta equal to 1, we rewrite the dispersion coefficient in the one-dimensional case, which has this form. These 2 multiplicative terms are smaller in this case. And this formula could be rewritten is minus the homogenized coefficient in the one-dimensional case, the average of the square of this function, which I call here xt. The characterization of Q1 and D1, the homogenized and the Barnard coefficient in one-dimensional case, are given in this theorem. Q1 has this form, the classical form, and D1 is minus Q1, the average of the square of xt, where xt is the self function defined, the self function that is solution of this differential equation. Where let us observe that on the right-hand side appear the characteristic function on the subset T. As we can see, Q1 does not depend on the microstructure. Nevertheless, D1 depends on the microstructure, and dependence is through the function xt. Since we want to study the variation of D1 when the microstructure vary preserving the volume proportion gamma, let me introduce some notation. Since we work with microstructure, each microstructure will be represented through the characteristic function of such subsets T. And we denote by C gamma the set of those characteristic functions such that the measure of T is preserved, is gamma times the measure of Y. We also denote, or we introduce a notation, J0 is quadratic functional and is the average of xt square, where the average of xt square. With this notation, the dispersion coefficient D1 in the one-dimensional case is minus Q1, this quadratic functional J0. And let us observe, looking to this formula, that looking for the extreme value for the dispersion coefficient is proportional, or the extreme value of the dispersion Barnard coefficient are proportional with the extreme value of the functional J0. So from now on, we are looking for the extreme value for the functional J0 on this set C gamma. Since C gamma is not a compact set, we need to relax our problem, and we denote by D gamma the closure in L infinity of C gamma. And we extend our quadratic functional J0 to this functional J, which is J of theta is the average of x theta squared, where x theta is solution of a similar problem, but on the right-hand side, instead of the characteristic function, appear theta, appear the continuous function theta. With this, we get the first result, or our result. Given in this theorem, the first two identities are the classical in optimization and relates the extreme value, or relates the original problem with its relaxed version. And the third and fourth equality, we explicitly compute the extreme value of functional J. This result has been published some years ago. Using this result, we get corollary, which tell us that the set of dispersion when the microstructure vary preserving the volume proportion gamma is included in this interval, where the ends point of this interval are exactly the extreme value, of course, multiplied by minus Q1. And let me represent graphically these things. On the horizontal axis, we consider the volume proportion gamma. And on the vertical axis, we consider the dispersion. The maximum is 0, and the minimum is what I call here the mean, and I represent graphically by this red curve. Looking to this inclusion and to this picture, the dispersion for different microstructure has to be somewhere in the yellow region, including the red curve. I insert red points in those positions where we can find the dispersion coefficient for some microstructure. The question that we asked for was the following: which is the entire red zone? Or mathematically speaking, does the inverse inclusion hold or not? And the question and the answer is what represents our second result in a one-dimensional case. And yes, the inverse inclusion is true. This means that D1 fills up the entire interval. And I represent the entire red zone is the yellow zone union the red curve. Using these results for the one-dimensional case and the previous computation that we have done, one could easily obtain the results in the case of laminates. I recall you that dispersion in laminates were two multiplicative terms. The first one were depending only on the dimension, or depending on the dimension and not on the microstructure. And the second one, which is this one, is depending on the microstructure. And for the laminates, the result is given in this theorem, and we obtain a similar result. The set of dispersion for laminates is equal to this set. And this result was published in 2012. Let me finish with some open problems. I spoke about the one-dimensional case and laminates. The higher dimension is still an open problem. We think that interesting particular case could be the spherical hashing structures, or some material with I don't know, ellipsoidal geometries. And of course, the final aim is to find bounds for the dispersion coefficient in higher dimension. Thank you very much, and I would like to say happy birthday, and of course in Romanian also la mulți ani. And here is a picture that we took some years ago when I defend my thesis in Santiago de Chile, and this is also. Thank you. And thank you very much.